Ladies and gentlemen, welcome back. Last time we took apart a board out of a Samsung induction stove and found the board was not repairable. It had taken a 400 volt hit right through all of the low voltage chips. So we have another board here that's blown up the same way, but not as bad. The low voltage chips did not get killed, I don't think. So we'll see if we can pull some parts off the dead one and put it on the live one. These are the two big resistors that feed power into the main inverter section. They were blown off the board and the remains were actually welded to the traces. So I had to Dremel them flat to get the resistor remains off. And then they came down flat enough that I think we can attach new resistors to them. So to start, we'll just find out what components are actually dead on this board. So we'll test all the support components around the IGBTs. Both the IGBTs were fried, of course. So here we're finding resistors that should conduct and don't conduct. Just working our way through the support components here. These resistors here, you notice there was a 34 ohm reading. The two resistors and the diode that are in parallel here. Each resistor is 68 ohms, so two of them in parallel, of course, is 34 ohms. This here has a diode in parallel with a resistor. So I'm checking it in diode mode and then I'm checking it in resistance mode just to make sure that both of them still work. It's a 4.7K resistor, so you can see there was 4694 or whatever. That's perfectly good. I couldn't get a reading off this capacitor, probably because it's in parallel with the resistor, but given that the other two components are fine, I wasn't worried about it. So this is a thermistor for temperature monitoring of the inverter stage here. It's unlikely to be damaged. The power does not go through that part of the circuit. And this we're just testing that the inverter section is not shorted out, even with the IGBTs removed. So now we'll check the support components on the other IGBT. This is 7.5 ohms, as you saw. Two 15 ohm resistors in parallel. Those were blown up on the other IGBT, but this one, they seem fine. And there's a pair of 68 ohm resistors. Reading is 34, just like they should. And again, the diode measured anyway, although 34 ohms that's in parallel with the diode makes it impossible to get a reading off the diode. But if the resistors are fine, the diode is fine too, I'm sure. It's not dead shorted, which is how a diode often exhibits. And here, same as the other one, we have a 4.7K resistor in parallel with a Zener diode. In this case, the diode, or the resistance, is high enough that you can actually read the diode in one direction, and then in reverse you'll be reading the resistance. So now we'll move on to the driver circuitry. Oh, sorry, before we do that, these are the feed resistors for the other inverter stage, which was undamaged. So we'll just check them, make sure there's no damage here. These are 10 milliohm resistors, so it's too low of resistance for my main fluke meter to read properly. So we'll use a milliohm meter, and as you can see, two 10 milliohm resistors in parallel is reading the correct 5 milliohms. So these are undamaged. So now we will test the driver circuitry. First thing we'll test is whether VDD and VSS are shorted to each other. We see we've got 300 and some kilo ohms here, so that's really good. What you don't want is 0 or close to. The other board was 20 ohms, I think it was. Now we'll check the input from the controller. And there's two lines coming in from the controller, and they go to pins 1 and 2, which I'm just showing you where the traces run here, to those little tiny resistors. So the first thing we'll do 4 sets of tests. First one, we'll put the negative probe on VSS or ground, and we'll check each of the 4 lines. What we're looking for is uniformity. So you will notice a slight difference between left and right boards because the left side does not have a driver chip installed, so it'll change the readings a little bit. But what we're looking for is the two on the left to be the same and the two on the right to be the same, and everything to be sort of close. So now we'll swap the leads around and we'll put the positive lead on VSS and we'll check all 4 lines again. And now we'll do the same for VDD. So we'll take the negative lead, we'll put that on VDD, which is pin 7, and we'll check all 4 lines. Got about 1.5 volts of drop, which is good. Okay, all nice and uniform. And finally we'll take the positive probe, put it on VDD, and we'll check all 4 lines again. Left and right, like I said, are a bit different, but as long as the 2 on the left are uniform, the 2 on the right are uniform, that's fine. Now we're checking the connection between the driver and the IGBT support circuitry. So these traces should go right through 0 ohms. Sometimes in a high power fault you will find traces blown. Usually you can see that, there's burn marks, but just to be safe we're checking them here. These are on the diagram as HO and LO. Hello. So we've checked both ends of the circuit. We've checked the IGBT support components, and we've checked the driver end, and other than a couple dead components, everything, the main parts seem to be alive, the controller seems to be alive, and so on. So now this is on the dead board. I'm checking to see if we have some donor components. We need a pair of the big resistors, so I get the milliohm meter out for that. 5 milliohms again. So these 2 resistors are usable. I did buy some resistors, but you can get them in either 2 watt or 3 watt. And because these are used basically as fuses on this board, I didn't want to use the wrong type. So it's better just to use ones that I know are the correct ones. So preheat the board just to prevent damage. Sometimes on a big board, when you introduce hot air like that, you can damage the board. The board sometimes will delaminate. So I prefer to preheat the board. It's basically just a little electric barbecue. And you can see we're removing the 4 resistors. We need the 2 big ones, and then there were 2 smaller, I believe it was 68 ohm resistors, or was it the 15 ohm ones that were blown up on that one IGBT. I'm pulling the controller off the board too. We'll test that later just to see if it is dead. I'm pretty sure it is, but we'll just test it later. Again, preheat. I like around 100, 110 degrees Celsius. That'll be somewhere north of boiling temperature in degrees Frankenstein. We'll pull the dead components off the board here. And then we'll, of course, use some flux. Makes everything go better with soldering up to a point. Some guys like using gallons of the stuff. That's overkill. You don't need that much, but it does help everything float and just makes life a whole lot easier when you're soldering. These large pads here, these are the ones I had to Dremel flat because they had pieces of resistor welded to them. You'll see me add quite a bit of solder to these pads, and that is because if there was any stress cracking or anything in the traces, I want to coat that with solder so that it won't be a problem. And also, just because of the way the damage was, it exposed more of the trace than was normally exposed for soldering to. So I'd like to cover that with solder, and just it adds to the current carrying abilities of that part of the trace. I didn't get crazy with it adding big gobs of solder, but there is more on there than you would normally use. You might worry that resistors wouldn't be able to dissipate heat properly into the board, but there is actually a little bit of gap underneath. The reason I'm saying this is because when I dremelled the pads flat, they still are slightly thicker than they would be normally. You would think that'd be a problem because the resistor's not in contact with the board, but actually you can take a piece of paper or whatever and stick it under a resistor that's from the factory. Like, there is a little bit of an air gap there anyway, so not a big worry. As long as the ends are anchored down good, that's where most of your heat is dissipated into the board. And just adding a little bit more solder to the one end there. And we try and leave them straight. Some guys, they don't care, they'll put them on crooked. It doesn't affect how they function, it's just, I guess, my OCD coming through. So we bought some new driver chips. One of them did need replacing, so we'll go ahead and get that out of the package. If you're ever wondering which way is up on these chips, there is a dot on the board. In this case, I believe it's a triangle, which marks pin 1, and then there'll be a dot on the top of the chip marking pin 1. And then usually the pin numbers will count around from that pin counterclockwise. So likewise on the controller chip that we pulled off the board before, it has pins on 4 sides, so there will be a dot on top marking pin 1, and then you count around in a circle counterclockwise from pin 1. You saw I touched the pads there with some leaded solder. Just makes everything go together easier than the lead-free stuff they have on the board from the factory. They have to do that for regulation reasons, but lead is just so much nicer to work with. Now clean up the board a bit. I always like to do this. Some guys, they leave flux all over the place and it looks like a war zone afterwards. I prefer somebody to really have to study the board to know I was there at all. In this case, being the board is blown up so bad, I mean, you'll be able to tell anyway, but it's just nice to be neat. Here you can see there was some arc gouges on this heatsink. I just took a little needle file and I filed over the big burrs so that there's no pokey bits hanging down. These tubes gave me a bit of a fight getting into them. So here you can see we have some new bridge rectifiers and also some new MOSFETs. These bridge rectifiers are a slight upgrade. It wasn't bridge rectifier's fault that it blew up. The IGBTs shorted out and the bridge rectifier was just collateral damage. Just checking here to make sure the packages are exactly the same size and shape. So the ones I got are actually rated for 1000 volts. Same current, 50 amps. I couldn't get the exact model number of the one that was in there, which was a 600 volt part, 50 amp. So I got one that's slightly better. I checked that the voltage drop was the same across them, so that if you have one with a higher voltage drop, it'll dissipate more heat for the same current. So this was the same, so it's not going to run any hotter than the original part. So this is actually folding pliers, they call it, for working with sheet metal, furnace systems and whatnot, HVAC. And it's got really smooth jaws on it. If you're adjusting the leads, you don't want to introduce nicks, especially with high power parts like this, because the nicks can over time crack and break. So it's best to pick something with really nice flat jaws, nice smooth jaws. And these are, I think, 3.5 inches wide, so they're easy to do a long part with lots of pins all at once. Just making sure that the angle is exactly the same. Not bad. Good enough for most of the girls I go with. And just test fitting everything, make sure it's going to fit flush to the heatsink. You don't want any stress on a part because it can cause one side to lift away from the heatsink, and then you don't have thermal contact and your part will burn up. So make sure everything fits really well. This was kind of a obnoxious way they have this, because it's like a 45-degree angle that the heatsink face is at, so it's a little extra tricky to make everything fit. These IGBTs are a slight upgrade to what was in there. It's the same manufacturer and the same product line, but these are 65 amp models. The ones that were in there were 50 amp, and especially because this circuit seems to be under-engineered, not quite up to the task of what they're asking it to do. I felt it was probably best just to upgrade the IGBTs slightly, and hopefully it won't have this problem again. So the only difference is for the same, like the package is limited to how many watts of heat it can dissipate. So basically a higher binned part like this will run cooler at a certain current flow, which is to say that this pair of IGBTs should run slightly cooler than whatever was in there before, hopefully extending its life. So here we go with my favorite heatsink grease. Hate this stuff. This tube is also a little on the old side. It's getting kind of stiff, but it's good enough for what we need here. If this doesn't work, I don't think there'd be any problem with using the stuff they use for CPUs and computers. I mean, its whole purpose is just to conduct heat between two flat surfaces, so it should work just fine. But this is the stuff they had in there, so I'll use this. So you don't need a huge thick layer, as anybody who's ever put a CPU in a computer knows. You need just enough that it's going to squish a bit when you tighten that screw up. I like to do a series of straight strokes across just to level everything out, and to provide a little escape paths for any trap bubbles. as everything is squishing together. And make sure you don't get any on you, or you will always have this stuff on you. Not quite as bad as molybdenum disulfide grease on a white leather couch, but it's close. Don't ask me how I know that. So this was the only screw with a washer on it to spread the force out a little bit. And now we're very carefully going to mount this up. Turn the heat sink a little bit so you can see there. I'm really not putting any force on this at all yet. I'll tighten it down later after I'm sure everything's straight. I'm just grabbing the shank of the screwdriver. I'm not twisting by the handle at all. You can see it's starting to squish out the sides there, which is good. And here's where there's a bit of a problem. I thought I could just sneak that heatsink underneath the two IGBTs that are still left on the board. But with the long leads on the bridge rectifier in the middle there, I can't make it work. So we'll pull the two IGBTs off the board, then we'll install the heatsink and the bridge rectifier, and then we'll start adding in the other components. Not a big deal, just a little extra step. Time to use my favorite tool again. Turn it on, that helps. Because there's so much copper on these boards and such thick traces, we're going to have to set the temperature quite high. In the meantime, while we're waiting for that to heat up, I'll tidy up a little bit. This isn't sped up, this is how long it actually takes. Forgot to turn my mic on so you don't get the benefit of the sound, but there you go. Ready to reassemble. So now we'll just check that leads and everything are pointing straight up and down so that it goes into the board easy. And then we'll tighten the screw up there a little bit so it doesn't move around a whole lot. Give the desoldering gun a quick cleanup before we put it away. I don't think I showed this last time, but this is the barrel that all the solder crud is collected in. You can see it down on the bottom there. It's all formed into a ball. Just give it a whack in the garbage can and good to go again. Just doing one last test fit here from the proper direction. Make sure everything's going to go together smooth. And it did, so it's time to start putting the screws in and put everything back together. Making sure everything is right, dead straight. And it is, so we'll tighten the screws up. I actually tighten each of these screws up twice. I tighten them up and then I go back, loosen each one off, then retighten it. Just something I do. The things can move around as you're tightening them, so just making sure there's as little stress as possible on everything. And there you can see it. This is the final time that heatsink will be off. So this is the normal way to mount big transistors to a heatsink, is these little silicone gaskets. I have a kit of a bunch of different sizes there. So just finding the correct size. These are, I think these transistors are TO247 package. Bigger than TO220. I think they're TO247s. Just making sure all the mating surfaces are clean. That's IPA, isopropyl alcohol. It's important, you see the back of the transistors there is metal, but you don't want that in electrical contact with the heatsink or it'll short out. So that's the purpose of the silicone gasket, is to allow heat transfer but not to allow electrical connection between the two. If you remember from the last video, Samsung has some kind of glorified wax paper they put in between, which is single use, and I've never seen that particular mix before. So we'll just put it together like everybody else does. It's working in plenty of other devices that are run at a lot higher power than this, so this, using the common technology in this case, will be sufficient. See, I forgot to put the gaskets under the first two. We'll come back to them. All of these just fall in. There's no resistance at all on the pins, which is good, but you want a little bit of play there because you tighten everything down, as mentioned, to the heat sinks really tight, and then the mating surface is right flush for good heat transfer. And then the pins, there's a little bit of play. The pins in the hole can move back and forth a bit, and they can be soldered in whatever position, right? So you want, the main thing is you want good thermal conductivity to that heatsink, and then whatever position the pins are in, they just get soldered that way. If you do it the other way, where you solder everything first and then you try and mash the transistor over so it meets the heatsink, you will sometimes have problems, because you'll have an air gap there, and at this power level it doesn't take long to burn up a transistor if it gets too hot. You see these goofus clips they use there. Most companies will just put one screw through each transistor. What's wrong with that? But Samsung's got to get fancy here for whatever reason. I guess screws are expensive and clips were cheaper. It's kind of a pain in the butt to put together, but whatever. I'm just making sure those silicone gaskets are nice and square in their proper place, and then we'll cinch that clamp up. This clamp is made to bottom out against the heatsink surface in the middle there, so I tighten it down good. There's no reason not to. That spring tension will be calibrated for whatever Samsung felt the proper pressure was to hold the heat sinks against the transistors against the heatsink. And here I'm going back and fitting that gasket in there that I forgot. It is important to keep the gaskets and the mating surfaces clean. If you get a little chunk of something, it can puncture through the gasket. Worst case would be a little piece of metal or something, which could also conduct electrically between the back of the transistor and the heatsink. That would be very bad, so try and keep everything as clean as you can. Make sure everything's cinched down tight. You don't want to go whole hog on the bridge rectifier in the middle there, because you can break them. So don't go crazy on that one. But in the other case of those two clamps, it was possible to tighten them up fairly good. Now we'll just solder everything back. You see I clipped the leads part way through there. I forgot to do that before. When you get new transistors, they come with quite long leads, and you cut them to whatever length you need. And there's the finished product. Not terrible, I don't think. And clean up all your flux residue. I don't like leaving that stuff around. It just looks bad. I am going to come back and conformal coat this board again, because there was originally a coating on the bottom. I don't think I showed it in these pictures, but I did do that. So just checking to make sure all the solder joints are good. You can see where the conformal coating has been removed when I used the Q-tips and the alcohol there. Like I said, I will come back and conformal coat the bottom, and then you'll hardly be able to tell. So there we are, back together, ready for testing. Now, the controller from the last board, dead board, I just wanted to check a couple things with a meter here. The left pin is on a VSS or ground. This pin here, pin 29, which should be one of the IGBT outputs, is dead shorted. Measuring the bottom here, the 15th pin, the second from the right there, that is supposed to be ground, so that's 0 ohms. Pin 16, however, is VDD, or plus whatever, 3.35 volts, whatever the controller takes for power supply, and that should not be shorted to ground rather. So yep, she's done. So we'll package this up and we'll send it back to the guy, and we'll see how that goes. It was fortunate that this gentleman had two of the same boards to work with. We could have repaired this one without using donor parts. Unfortunately, the first board was completely beyond repair. Sometimes that happens. Here you can see I was putting it back together. The board is on the right, and it works. So, another successful fix. Thanks for watching.